Welcome to lesson 3 of year 2 pure mathematics chapter 6. This is trigonometric functions, and today we're going to apply what we know about sec, cosec and cot to proving identities and solving equations. It's the same prerequisites as before, so we're going to be using some of the ideas that you met in year 1. Right, so without further ado, please pause the video and try the 4 warm-up questions. Okay, and we'll have a look at the solutions now. So our solution to question 1, we have to write these two algebraic fractions as a single fraction. So in other words, combine the denominators. So we look at the two denominators here. The way to find a common denominator, of course, between these two expressions is, of course, to multiply them together. So we can straight away write this as a single fraction. We've had plenty of practice at this. So this is going to be equal to something over the product of x and 1 subtract x. Okay, just simply multiplying these two expressions together. When we do that, we have to compensate and keep the fraction in proportion. So we think, what have we multiplied the numerator by in the first fraction here in order to generate this expression here? Well, because the denominator is 1 subtract x, that's already present in the denominator, but we have multiplied it by x. So we have to include an x now in the numerator for that one. If that wasn't clear, just let me reiterate. If you times top and bottom by x, it changes nothing about the fraction, but we now get a denominator of x multiplied by 1 subtract x, which is what we need. Similarly, in the second fraction, we need the product 1 subtract x in the denominator, which means the numerator would also have to be multiplied by 1 subtract x. Okay, so that's how we establish a single fraction here. So it's going to be x plus 1 subtract x. 1 multiplied by 1 subtract x is just 1 subtract x. All right, and then we can see if we can collect some like terms. Well, it's pretty clear. I think the x's are going to cancel. So we're going to be left with 1 over the product x multiplied by 1 subtract x. Okay, and we now have a single fraction. Moving on to question 2. We're asked to explain why the equation cosec equals 2 and x is any real number. That's obviously important. They've bothered to tell us this, that's important. And why it has no solutions. Well, this is just a fundamental fact about the cosine graph, isn't it? I won't draw it out. We can just simply talk about the range. Okay, so consider the range of the graph y equals cos x, where x is a real number. And we know the fact that what I'm talking about is that cosine is sandwiched between and including -1 and 1. Okay, so the fact that we're told the equation cos x equals 2 has no solutions, well, the simple reason is because that 2 is outside of the range of the cosine graph. All right, so this is the range, and we can just say that 2 is outside of the range of y equals cos x, where x is a real number. We have to stipulate that, because if I somehow restricted the domain, we might have a situation where the range would be different. For instance, if we restricted the domain between 0 and pi over 2, then the range would would be 0 up to and including 1, okay, including 0 as well. So we just have to be careful about that. But that's the long and the short of it. I mean, the main issue is just that the range is the range of cosine. Okay, that's what causes this equation to fail. Okay, there are complex solutions to this, but we're not going to go into it in this course. So for question 3 of the warm-up, we're asked to solve a trig equation in the interval 0 to 360 degrees. And we're given the equation here. It's quite straightforward. It's just a case of, can we apply what we learned last year about cast to get the correct number of solutions? Well, first thing to realize is we need to find our principal angle. So let's write that up. So the principal angle . Now, remember, the principal angle is always an acute angle. And if you work out the principal angle and it's not acute, then you've done something wrong. And the way we get this is we take our principal angle, which would be x, as the inverse cosine of the square root of 3 over 2. Now, there's a couple of things here to mention. I'm literally just solving the equation, okay? The equation that's given here. I'm just solving it. But notice I've made a slight adjustment. I've not made a mistake. I've dropped the negative sign. So the negative sign that appears here has to go, okay, when we're finding the principal angle. The reason is because we need the calculator to return an acute angle, and all trig functions are positive in the acute section, i.e. between 0 and 90. So I drop the negative. So I'm just going to make a note of that. It's incredibly important that we remember to do this. I might have said this over and over again, but it's worth saying yet again. So ignore the negative sign. If you don't recognize the inverse cosine of root 3 over 2, don't worry, you can use a calculator. I've got it set to degrees. So if we move over to the calculator, I can simply do shift cosine, so inverse cos, and then it's going to be the square root of 3, just come out of that, or you can write it as a fraction, it's up to you, divided by 2, so it actually looks exactly like what I've written on the board, and press equals. We should get a nice answer, and in fact we do. It's a standard answer, isn't it? So this is our principal angle, 30 degrees. Notice it's an acute angle. Okay, so therefore x is equal to 30 degrees. And we have it. Now, that would be one of the solutions, perhaps, okay, not necessarily. This is the angle that we now transfer to the cast diagram, and the cast diagram will give us the solutions we need. So I'm going to draw a cast diagram now. So I'll put that here. I've got plenty of room. So CAST, specifying which trig functions are positive in which quadrant. We start at 0 and we work anti-clockwise in the positive direction. Now then, this is where we use the negative sign. So remember, I dropped the negative sign a few moments ago here, okay? The cast diagram will deal with the negative sign for us, okay? If I put it in the correct quadrant, we should be okay. So I know for a fact that my cast diagram tells me that all trig functions are positive here, and that cosine is positive here. All right. So if I put my principal angle in those two quadrants, that wouldn't be correct, because that would be the positive version of root 3 over 2. So i.e. just root 3 over 2. So the quadrants we need are sine and tan, where that value is negative. Okay. So we put the principal angle here and here because it's negative root 3 over 2, not positive root 3 over 2. So we have 30 degrees there, 30 degrees there. And we can now read off all the angles between 0 and 360 degrees. Now remember, of course, if we go a full circle around the cast diagram, when we get back to this point here, we'll have gone 360 degrees. So it's just a case of jotting down all the angles that we find in between. So my x values are going to be, well, if I went halfway to this point here, that's 180 degrees. But I don't want to go that far. I only want to go up to here. So it's 30 degrees less than 180. So that's going to be 150 degrees for my first angle. And then my second angle is 30 degrees greater than 180 degrees. So that's going to give me 210 degrees. Okay. And there's just two solutions between 0 and 360. So that should do it. Now we can just check our answers here on the calculator, just so you can be really confident that you've got them. So if we do the cosine of 150 degrees, okay, we get negative root 3 over 2. That's correct, okay? And we cancel that. Let's do the cosine of 210 degrees, which is, again, negative root 3 over 2. Now, let's say, for example, you'd made a mistake. If you put it in the wrong quadrant, you would be doing the cosine of 30 degrees, okay, which gives you positive root 3 over 2. Now, notice the mistake here. That's not what we wanted. We wanted negative root 3 over 2, okay? So that would have been wrong. You'd be able to check on your calculator and see that you're wrong. Another way you might have been wrong is if you'd have put the 30 degrees in the other positive quadrant, the C quadrant. So if I did that, I would be doing the cosine of 30 less than 360, which is 330. And if I do that, again, I get positive root 3 over 2, which is not the answer I require. Okay. So just a little bit of revision on cast and solving trig equations in degrees. Now for the final question, number 4, we're going to be looking for values of theta between 0 and 2 pi this time. So we're now in radians. This is implicit in the fact that it's written in terms of pi, and we're solving this equation. So we've got to be a bit careful here. Now, the first thing we need to do is make sure, if we're going to use a calculator to assist us, that the calculator is set to radians. Now, you might be able to see on the screen, I hope you can, that the calculator is in fact set to degrees. You can see the little d there. We don't want that. We need radians. Now, the way to change your calculator setting to radians is as follows. So if we press the shift key and the menu key, that will take you to setup. Number 2, option 2 is the angle unit. So select that and then just select option 2 again, radians. And then you'll notice that the symbol is now changed. Okay, the degrees have gone and we're now in radians. All right, so we're now ready to start. So let's go back to the question. We need to find our principal angle again. So let's write that down. And in finding the principal angle, remember we simply solve the equation. Okay. Now, just to be really clear, we're dealing with 2 theta in this instance. Okay, not theta or x, 2 theta. So perhaps I should make a substitution before I proceed. So we'll say, let big X equal 2 theta. So in other words, we're going to be solving the equation sine of big X is equal to root 3 over 2. So it's the first step that I almost missed out then. So for the principal angle, we just find out what big X is equal to. So I do the inverse sine of the square root of 3 over 2. Now, you'll notice the key difference between this question and the previous question is that we don't have a negative sign to concern us. So I can just go straight to it. And again, if you're not comfortable doing this in your head or drawing a small sketch of a right angle triangle with 30 and 60, you can just use your calculator. So shift sine, so that's inverse sine and then we put the square root of 3. Let's come out of that. Square root of 3 over 2. Just make sure it mimics what you've got written on your paper. And we get pi over 3. Okay, now at this point, you might not like to be dealing with hang on a sec, sorry, just made a mistake here. So you might not want to be dealing with radians. That's completely up to you. It depends what you're comfortable with. Let's write it down first of all. So x is going to be pi over 3. Now, if you don't like dealing with radians, we can change this into degrees rather simply. Remember, for changing between radians and degrees, you simply just swap out the pi for 180 degrees. So I'll do that. So this is going to equal 180 degrees, okay, divided by 3, okay, which is of course 60 degrees. Okay, so we can deal with a principal angle of 60 degrees. What we also need to do next is we need to adjust our interval. And we can convert to degrees as well. You've got a bit more space than I have on your page, but I should have enough room here. So if we change our interval to degrees, first of all, so 2 pi, remember, is 360 degrees. Okay, now we have to make an adjustment because it's not theta we're finding, it's 2 theta. Okay, so I need to double the whole thing. So if I change that to 2 theta, I've multiplied it by 2. Okay, and if I double 360, you'll get used to this. You'll get 720. All right, so therefore, when we're dealing with this x angle that we found 2 steps previously, we're going to look for the x angles that will satisfy the equation in that interval, but the interval is going to be between 0 and 720. So that's 2 revolutions of the cast diagram. We're ready to draw the cast diagram now. So we'll do that. Okay, so this is all about x at the moment. We're talking about the angle x. So this angle. Okay, now the principal angle is 60 degrees. The value I took that from was positive up there. So I just have to look for where sine is positive because it's a sine equation. Okay, well, sine is positive in A quadrant and the S quadrant. Okay, so that's where I'm going to add my principal angle. So this is going to be 60 degrees and 60 degrees again. And don't forget, I have to go around twice. So I start at 0 and go in the positive direction twice. So now we can list all our angles. Okay, so we've got x is equal to 60 degrees first of all. Okay, and then 60 less than 180, which is of course 120. And then because we're going around twice, we just simply have to add 360 to both of those. So we're going to have 420 if you add 360 to 60. And 360 plus 120 is going to be 480. Notice we also have 4 answers, which gives us a good indication we've done this right. For every 360 degrees you go around, you would expect 2 solutions. Okay, so if you're going around twice, you'd expect 4. So notice, of course, this x, remember, is the 2 theta that we found earlier. Okay, so in order to get theta, we need to halve all our answers. So let's do that now. So theta is going to be half of each of these. So it's going to be 30 degrees half of that is 60 degrees, 210, and 240 degrees. Okay, now we have to pause here because we haven't actually answered the question. We converted between radians and degrees in order to make the process a little bit more familiar. So now we need to convert between degrees and radians. Now I can do this relatively quickly because if you remember, I'll just make a little note here. Pi radians is 180 degrees. Okay, that means that for every 1 degree, I can write it as pi over 180 is what 1 degree is. So to get any angle you like, it's simply the angle multiplied by pi over 180. So in other words, you take the degree as a fraction of 180 and then just simplify it and then multiply it by pi. Now, we've actually got an answer already staring at us from previously. So we know that 60 degrees is pi over 3 from earlier. So they're equivalent. So my theta, okay, I'll put that in first. So that was pi over 3. That's 60 degrees, which makes sense because one third of 180 is 60. Now, 30 degrees is half of that. So half of pi over 3 must be pi over 6. Okay. Then if we look at 210, 210 is 7 lots of 30 degrees. So that must be 7 pi over 6. And the final one, 240, is 4 lots of 60 degrees. Okay, because it's 6, 12, 18, 24. So 4 lots of pi over 3. Okay, and that will give us all 4 answers as radians, as required. Okay, so before we get started on the worked examples with the proofs and solving equations, just compiled some of the facts that we've met already. One thing I've omitted are the new Pythagorean identities, but we're going to talk about those in the next lesson. So I just want to stress that all this information can be derived from these right angle triangles based on the unit circle. So you've got your 2 identities that you met last year, just here. They're going to be really useful. And we've also got these reciprocal functions as well. And I'm just stressing here that 3rd letter rule. So the 3rd letter of our reciprocal trig functions corresponds to the 1st letter of the original function, but reciprocated, of course. All right. And then we also touched on in the last lesson the fact that because tan over here can be represented as sine theta over cos theta, then because cot is 1 over tan, as we can see here, then combining those 2 ideas, we also have that cos theta over sine theta must be the same as cot theta because it's the reciprocal of tan. And to reciprocate tan is simply to switch sine theta and cos theta around. So there's some basic ideas there that we're going to be using. And once again, if you're more interested in the Pythagorean identities that we met last lesson, that were derived last lesson, they'll be coming up a bit later on. So let's move now on to the worked examples. Right, so for the first one, I've given you plenty of room to do this because it might take quite a few steps, and I'm going to try and navigate around the space I've got on the screen here. It's a proof, the first one. We've got to prove this identity. Now, identities, as I've stressed previously, the way to do it is not, first of all, not to rearrange the identity. So you do not multiply both sides of the identity by cosec theta. Okay, that's not the way to do it. You're not allowed to manipulate the between one side and the other side, so between the left and the right, in any way. That's not allowed. You can do that when you're using known facts such as sine squared plus cos squared is identical to 1. that can be manipulated. But when you're proving an identity, you simply have to show that the left-hand side logically implies the right-hand side. So we're going to begin with the most complex looking side, and we're going to break it down, hopefully, into something more simple. And that's the easiest way to attack this. Okay, so start with the more complex side. And I think you'd agree with this, that the left-hand side is the way to go. So I'll just make a note of this. So starting with I'll put that in inverted commas. This is just my opinion, of course. So the more complex left-hand side, there might be situations where there isn't much between them. Okay, but clearly we want to show that the left-hand side is in fact a representation of sec theta. Okay, now this is going to be my first piece of advice before we get started. So I'll just write, we're going to show that the left-hand side implies that the right-hand side is true. Now, my advice to you is, because we're dealing with trig functions we know and reciprocal trig functions, let's get everything in terms of sine and cosine, which are the basic building blocks of these functions. That way, we can see commonalities and hopefully we can start bringing like terms together. But that's my advice, okay? So I'll put that here as something important. So advice, write every term on the left-hand side in terms of sine and cosine. Okay, even tan can be written in terms of sine and cosine. They are the basic building blocks. All right, let's do this. I'm going to start this up in the top right hand corner. Okay, so the tan theta, I'm going to replace that with sine theta over cos theta, first of all. So that's just making a conversion between this and this, that they correspond. Okay, so that's my first sort of switch, if you like, my first substitution. Now, we also mentioned previously about cot. Okay, so we're going to be adding cot theta. Now, cot theta, remember, is the reciprocal of tan theta. So I can write cot theta as follows. I can write it as cos theta over sine theta, like that. Okay, and that's corresponding to the cot theta here. Okay, so I've just made substitutions based on the facts we already know. Now, cosec theta, again, using that third letter rule, which you're hopefully getting used to now. The third letter here is, of course, S. Now, that reminds us that this is 1 over sine theta. So I'm going to write that in my denominator. Okay, and you might be thinking, well, this looks worse. Well, it will look worse temporarily, and then until we clean it up, so you'll see it all fit together. So that the denominator is now going to be 1 over sine theta. Okay, now this is the first thing. So we'll start with the left-hand side is identical to that. Now, the next step, we're going to do some manipulation of this. Now, you notice that we've got coses and sines in the denominators. Now, we need to clear those, and we've got fractions over fractions. So if I multiply the numerator and the denominator of the large fraction by sine theta and cos theta, maybe perhaps we can clear some of this. So let's do that. So I'm going to multiply, just make a note, I'm going to multiply by sine theta, first of all, to clear some of these fractions. Now, when we do that, what's going to happen? Well, the numerator on the top left-hand fraction is going to become sine squared theta. okay, over cos theta. All right, that's multiplying that by sine theta. And then I'm going to have cos theta sine theta over sine theta. I'm just going to stress again what I'm doing. So I'm taking all this, multiplying it by sine theta, and then I'm going to take the denominator and multiply that by sine theta. I have to do the same to top and bottom because I don't want to change the fraction in any way. So let's do the denominator now. So that's going to become sine theta multiplied by 1 over sine theta will give me this. All right, now hopefully we've got some cancellation going on, and yes we do. So let's see what cancels. Well, this is going to cancel down to just 1 over 1, which is just 1. Okay, and then we have sine theta's cancelling here. Okay, so we can now rewrite this step a little bit better. So we've now got sine squared theta over cos theta plus cos theta. Okay, because the sine thetas cancel. Now the denominator cancel down to 1. Okay, so I'm essentially done. I could, in theory, write this all over 1, but there's no point, is there? Okay, I've just got that numerator because the denominator is simplified to 1. So we won't do that. Now, the other thing to notice now is we've got something that looks a little bit complicated, and we're trying to get towards sec theta. Now, you might be looking at this and getting a bit worried, thinking this is going in the wrong direction. But the thing to notice now is we've got 2 terms, okay? And I want to get it down to just 1 term. So the sensible thing would be to combine the 2 terms into 1 term, because my answer, my sec theta, is just 1 term. So at some point, these are going to have to be added together. Now I can do that because I can simply find, again, a common denominator, and I can add them both as fractions. So we'll leave the left-hand side one as it is. So this is going to be sine squared theta over cos theta. But the second term, if you'll notice, I've got to make this into a fraction. So it's got to be over cos theta so I can combine it. Now, if I multiply the bottom by cos theta, the only way to make this identical is if I multiply the numerator by cos theta. Okay, so I'd have to multiply top and bottom by cos theta, and this will give me cos squared theta. Okay, I hope that makes sense. You'll notice that cos squared theta over cos theta will simplify to the cos theta that we have here. Now, we've got the same denominator. Great news. We can now combine both fractions. So we can write this as a single fraction now. So this is going to be identical to sine squared theta plus cos squared theta all over cos theta. Right. We've got the single fraction. The numerator looks awful, but if you know your identities, this is actually great news. So we've now got a numerator sine squared plus cos squared. What does that remind you of? Well, if you go back to your known facts, it's the famous identity from last year. This is just identical to 1. So I can simply replace this now with 1 over cos theta. And I won't write any more because we can now see that 1 over cos theta is the sec theta that we wanted. Okay, In fact, why not? Let's write it in. There we go. Just enough room. Right. So there's quite a few steps there. The advice, again, is to get everything into the sine and cosine building blocks, and then look at the terms you've got. Does your right-hand side or the least complicated side, the thing you're aiming for, have one term, two terms? What does it look like? Do you have to combine them at some stage? But the easiest way to do that is to make sure everything is in terms of sine and cosine. Now, that's part A. So we've got a little bit more to do here. So again, I've not labeled the questions very well, so we'll do part B down here. This was part A up here. We have to explain why the equation given to us here has no solutions. Well, common sense tells us that we're going to use the previous result. And even if the previous result didn't work, you didn't manage to prove the identity, we can still answer this question. Now, notice the subtle difference between this question and the previous question. Okay, it's almost the same, except we've got these two coefficients here, as in two twos. Okay, 2 multiplying the entire numerator. Now, if I just sort of emphasize that in part B, I can factor out the 2. So we've got 2 multiplying tan theta plus cot theta. Okay, and that's all divided by cosec theta. And apparently this is going to equal 1. Well, if I divide both sides by 2 now, which I'll do, I'm just going to cheat a little bit. Actually, no, I won't. I'm going to write it out again properly. So therefore, we now know that tan theta added to cot theta divided by cosec theta is in fact 1/2. If I divide both sides by 2, that's what I'm going to get. And we can use the previous result now. Remember that the tan theta added to cot theta divided by cosec theta is identical to sec theta. So using part A, sec theta must equal 1/2. Now, we have got to explain why this has no solutions. Okay, why does this have no solutions? Well, the answer lies in the previous lesson when we looked at the graphs of sec, cosec, and cot. Now, just to clarify this, if I haven't seen the previous lesson, or you can't remember it, or you don't have your notes handy, let's just have a look at the sketch of sec theta first. Okay, so what I've done here, I've just sketched the graph of y equals cos theta with theta in radians. I've just looked at a small domain between 0 and 2 pi just to make the point here. Notice, of course, that this was discussed earlier, that the range of cosine is between -1 and 1 inclusive. Now, to get the sketch of sec, remember sec is 1/cos, all right, because of that third letter rule there. Now, to sketch the sec graph, remember the asymptotes of the sec graph, which remember all 3 of these reciprocal functions have, occur when cosine is 0. So you put the asymptotes down here, where the cosine graph is 0. So in other words, if you know the graphs of sine, cos, and tan, you can automatically or very quickly derive the graphs of sec, cosec, and cot. Now, the other thing to remember is, of course, that 1, which is the maximum point, and -1, the minimum point, is a feature of both cosine and sec, and they invert at these points. So the sec graph will go up like that and down there and go up there. Okay, so just to make this a little bit clearer, and get rid of the cosine curve, get rid of that. And now we have the graph of sec theta. So y equals sec theta. And there's nothing wrong if this was an exam situation. There's nothing wrong with doing a little sketch like this just to emphasize your points or just to jog your memory a little bit. So we need to answer the question, why does the equation sec theta equals to 1/2 have no solutions? Well, we can see from the graph that sec is not defined for all values between 1 and -1. It's that simple. So if I plotted the graph of y equals 1/2, which is essentially what we need to do, which would go somewhere across here like this, it's never going to intersect the graph of y equals sec theta. So in other words, sec theta and 1/2 can never coincide. So the simple explanation would be that y equals sec theta is not defined for the interval between -1 and 1. And notice that -1 and 1 are not included in that interval because -1 and 1 are actually in the range of sec theta. Okay, so you could also you could state that the range of sec theta is any value greater than or equal to 1, or any value less than or equal to -1 would be another way of saying the same thing. Okay, so in other words, you've shown that there's no solutions. Worked example 2, we have another proof, and once again we have the left hand side as the more complex side, and we have to show that that indeed is equal to sec x. Okay, so just as a little note, let's just state that. So we're going to show that the left hand side naturally implies the right hand side. Okay, so at no stage in this proof will you be writing both sides of the identity. That's not how it works. You show that the left hand side is in fact the same as the right hand side through a series of steps. So I'll just write it out again. So we've got we've got sec x plus tan x divided by 1 plus sine x. Okay, now what can we do next? Well, the interesting part about this is we're mixing up reciprocal trig functions and ordinary trig functions. But remember what I said in the previous example. It's a good idea. So advice again, write each term in terms of, that's not an oxymoron, I don't think it is, in terms of, in this case, sine x and cos x. Okay, the building blocks of these trig functions. So if we do that, we just have to use our third letter rule there for the sec, just to get you familiar with it so you don't have to keep going back. The third letter is, of course, C, so that immediately tells me this is 1 over cos x. Okay, so I'm going to replace that with 1 over cos x. Okay, now the tan x, and I'll just show you again that which corresponds to which. So this, the 1 over cos x is the same as, it's identical to sec x. And now we're adding the tan x now. Now tan, remember, the result from last year, that's sine over cos. So we'll write that in, that's sine x over cos x. So we have some correspondence here. So the tan x has now been substituted for sine x over cos x. And in the denominator, we can keep that as it is. We don't need to use anything complicated with the 1. We'll just leave that for now. 1 plus sine x. Okay. So we've got sines and coses everywhere. Now, once again, we should have one eye on where we want to end up. Okay, we want to end up with sec x. Now, sometimes it's a good idea just to walk backwards and think, okay, well, sec is the same as 1 over cos. Okay, so just a little note here. And then in some of these proofs, if you start with the right-hand side, and just as a little sort of bit of rough work, if you try and maybe rewrite the right-hand side as well, maybe the work you're doing on the left-hand side will meet the work you're doing on the right-hand side somewhere. Okay, and it might just help you to finish off the proof. Okay, but it's less important in this particular example. What is important is that we need to write this as a single fraction in the numerator if possible, because all this needs to simplify very quickly. Now, I don't like the cosines in those denominators, so I think a good thing to do here would be to multiply the entire thing by cos x, okay? And if I want to do that, I'm permitted to do that as long as I do the same thing to the denominator. All right, so let's do the next step. We're going to multiply everything by cos x. Okay, so we're going to have cos x over cos x plus sine x cos x over cos x. That's multiplying both the fractions in the numerator by cos x. Notice sometimes people make a mistake with that and they'll multiply the top and bottom. Okay, you're only multiplying the numerator by cos x. Now, if you're not sure why, a good example is if you took, let's say, a fraction such as 1/3, I don't know, and which would represent maybe the sine x over cos x or the 1 over cos x, it doesn't really matter. And if you multiplied that by, I don't know, 4, okay, we know from long experience that's the same as 4/3. It's only the numerator that is multiplied by 4, for the simple reason that if you did it wrong, if you multiplied 1 over 3 by 4 and you did the numerator and the denominator and multiply both by 4, it simply cancels down to what you started with. You've not actually changed the fraction in any way, which is why we're allowed to multiply the numerator and the denominator by the same thing, and it doesn't change the fraction at all. Okay, I just wanted to make a comment about that. I've seen that done before. When I think it's okay with numbers, but sometimes when we use algebra, it can become a bit more confusing. All right, so in the denominator, I'll leave the cos x on the outside, I think. So I'll put it here. So we're going to have cos x multiplying 1 plus sine x, like that. Okay, now it looks like we have some cancellation we can now take advantage of. So we've got the cos x is going to cancel, so that's going to be 1 and 1. And the cos x is going to cancel there, so that's going to be 1 over 1. So let's just write out the tidied up version. So this is going to be 1 plus, now the cos x have gone, so I'm just going to be left with sine x. Okay, and that's going to be divided by cos x multiplying 1 plus sine x. Okay. Right, now, what do we notice here? Well, we want 1 over cos x. Excuse me. This is what we're aiming for. Okay, and we've almost got it, haven't we? Now, look what we have here. We've got the numerator and this factor in the denominator are identical. That means we can cancel both out. So this will all cancel. This will all cancel, and we are left with the thing we wanted, which is 1 over cos x. And as we know, just maybe run out of room there, that's identical to sec x, which is the right-hand side. So we seem to have shown that. Now, for worked example 3, we have to solve our first trig equation using one of our new reciprocal trig functions, this case cosec. Now, obviously, you tend to use your calculator for these types of questions, and you'll be familiar with the fact that we don't actually have the sec, cosec, and cot buttons on the calculator. We're just stuck with sine, cos, and tan here, and their inverses. So we need another strategy. So the obvious thing to do is to use that third letter rule. We know that the third letter is S, so I can just simply rewrite this question as 1. In fact, I won't use green for that. We'll rewrite that as 1 over the trig function that starts with S, which is, of course, sine. It's 1 over sine x is equal to 4. Okay? And with one more step, we can break this down into a question that we're much more familiar with. So we're going to reciprocate both sides. So if I flip both sides, I'm going to get sine x is equal to the reciprocal of 4, which, remember, it's 4 over 1, so that's just going to be 1 over 4. So we've just rewritten the question, and that's it. I mean, you'll notice with maths, we're just adding extra layers of knowledge onto stuff you can already do. And we've now, with that new step, we've dealt with it, we've used our new knowledge, and we're now down to some nice skills practice from year 1. One thing to note, of course, is that we have an unusual looking interval from negative 180 up to 360, but the cast diagram will help us with that. So let's get straight into it. So we don't have a particularly awkward equation to solve. We can simply go straight into the principal angle now. Okay, there's no adjustment needed to be made for the interval. So the principal angle just do the inverse sine of 1/4. Right, now we'll use a calculator for this. This is a non-standard angle, and my calculator is currently set to radians. So I just got to decide whether I want this in radians or not. Well, the answer is no, because this interval has been given in degrees. So I'm just going to quickly change my calculator into degrees. So the way I do that, of course, is, well, first of all, I'm just going to rub out these. But what I need to do is just select Shift and Menu, which is Setup. Select option 2 for angle unit and option 1, which will take me back to degrees. Okay, and now I can do the inverse sine, so that's Shift and sine of 1/4, which I'll just write as 0.25, which is the same thing. And what do I get? So I've got a decimal. Now, just for the sake of accuracy, the exams tend to want your answers to 3 significant figures. Now, if I use 3 significant figures, I might lose a bit of accuracy here. So I'm going to use 4 significant figures, or in other words, 2 decimal places will be safe for now. Okay, so I'll just state that. So therefore, x is going to equal 14, and there's a bit of rounding to be done, 0.48 degrees to 2 decimal places. Okay, that's my principal angle. Now, now we've got that, we don't have any adjustments to make to the interval, so we can go straight to the cast diagram now. And let's draw that cast diagram. So we have C, A, S, and T. And now we have to just go back to the question. Now, we did change it from cosec x to sine x, but there was no change of sign involved. This was a positive number, wasn't it? Okay, so this This is a positive 4 and this is a positive 1/4. So we add our 14.48 to the positive quadrants for sine. Well, where is sine positive? Well, everything is positive in all, and it's also positive in S for sine. So positive and positive. So let's add the angle. So 14.48 degrees goes there. And in the opposite quadrant, so it'll be 14.48 degrees over there. Right, now we're just in a position where we have to read off our answers. So let's just establish where we need to start from. This is where it's a little bit unusual. We're starting at negative 180 degrees. Now remember, I usually write 0 degrees here and then just stipulate that we go anti-clockwise in the positive direction so that we get to 180 over here. And then when we get back to here, we're at 360 degrees. Now, in this situation, if we're starting at 0 degrees on this axis, okay, if I want to start at negative 180, I have to go 180 back. So this is the negative 180 is going to be here. Okay, so what I'm going to have to do, I'm just going to erase some of this. So we're going to start at negative 180, and we're going to move in this direction, still going anti-clockwise because that's the positive direction, but I need to start at negative 180. Now it's a superfluous detail. This what you'll notice is it makes no effect, or it has no effect on the answer, because there's no angles in the negative quadrant. So I can just simply say, okay, well, x is going to be, well, the first angle I get to, that I get to 0 here, and I've got no angles. So my first angle is, of course, just going to be 14.48 degrees. Okay. And then the next angle is going to be 14.48 less than 180 degrees. Okay, so we're now not at the negative 180. Now we're now at 180 because we've done a full turn. So that's going to be 165.52 degrees. And those are the answers, but we can just write those as to three significant figures, or to 1 decimal place. So therefore, I think we'll stick to 1 decimal place for this. So 14.5 degrees and 165.5 degrees to 1 decimal place. There's no accuracy stipulated for this, so I think that will do. And our final example today, example 4, we're going to put a lot of these ideas together now in solving an equation. So we have an interval in radians from 0 to 2 pi, and we have the cot function, okay? And we also have the cot of 2 theta. So there's a lot of stuff we need to consider here in order to get this correct. May also need a calculator at some stage for this, which I'll just bring into play now. Okay, and just to be aware, we could convert the calculator into radians, but if you prefer, which I will do, I'm going to convert the angles into degrees, work with degrees, and then convert to radians at the end. All right, and we'll just state that now. Okay, so we'll just state the interval. Oh, that's not a great color. So we've got 0 degrees, which up to 360 degrees, which corresponds to the 0 to 2 pi radians. Okay. Now then, we'll make the adjustment later. This is just an idea to get us thinking about degrees. Now, because we've got the 2 theta as well inside this cot function, we're going to have to make a substitution just to make life a bit easier. So we'll say let big X equal 2 theta. Okay, and we'll just rewrite the equation. So therefore, cot of big X is equal to negative 1 over root 3. Now, what we need to do now is we need to replace the cot X with something else. And we can use that third letter rule again. So the third letter of cot is, of course, T. And that means that cot is the reciprocal of tan. So we can now rewrite this as tan. So we've got 1 over tan X, tan of big X, of course, is equal to negative 1 over root 3. And to get something more familiar, we can just reciprocate both sides. So therefore, tan X, tan of big X, is the reciprocal of negative 1 over root 3, which is, of course, just going to be negative root 3. So we have a more familiar equation to solve. Okay, so now we're ready to find our principal angle. So I'll write this out. So big X is going to be the inverse tan. And there's something really important we need to remember at this stage. I hope you're all saying it with me. We're going to remove that negative, okay? The cast diagram deals with a negative, so we remove it when we're finding the principal angle. All right, okay. Just, again, I'll make a note of that just to stress it if you're revising from your notes later. So remove the negative sign. All right, so we've done that. And if we just go to our calculator now, and we'll calculate what this angle is. So it's the inverse tan of the square root of 3. And should be familiar on this one, but we'll do it anyway. So that's 60 degrees. Okay, that's rather nice. So we've got a nice looking answer. There's a bit of a giveaway in the question, which I'll get onto in a second. So X is equal to 60 degrees. If we just look at the question again, let's get this calculator out of the way. It says give your answers in terms of pi. Now that suggests if you're asked to do that, give your answer in terms of pi, you should be able to write your answers as fractions of pi, which suggests that the angles you're dealing with will be fractions of pi, i.e. nice answers. So 60 degrees, 30 degrees, 45 degrees, etc., etc. Just a little bit of a clue there. All right, so we've got that. We've got the 60 degrees. Okay, so now we've got our principal angle. We just have to make an adjustment to our interval. So that's the next job. So we're going to adjust the interval. Now, we've started writing out the interval. It's just a case of converting that into 2 theta. So we're going to have, just show you where I'm referencing from. So from this work we did earlier, here I just wrote it out in degrees, didn't I? Okay, so we just need to double everything. So it's going to be double of 0 is 0 degrees. And now we've got 2 theta instead. Gone for some bright colors for this, okay, and 720 degrees. So we're going to be looking in around 2 revolutions of the cast diagram. All right, so that takes us up to the cast diagram step. So we're nearly ready. I'm just going to move up to the right hand side. You probably have a bit more room than I do for this. Okay, so cast diagram. We'll put that on here. Like so. All right, and we've got to add our principal angle. Now, again, we've got to be very, very careful about this. the value we were given in the question initially was negative here. And when we changed it to tan, it's still negative. Okay. It's the principal angle where we don't use the negative. Okay. So we need to, because we're finding the tan of the angle of an angle, and we know the answer is negative, it must be in the quadrants where tan is negative. Well, tan is positive in T and A, so it's not those. Okay, it's the opposite. So tan is negative here and here in sine and cos. So that's where we add our angles. So I'm going to put that on there. So that's going to be 60 degrees in that quadrant, and in the diagonally opposite quadrant, 60 degrees. The angle is always given to the horizontal, okay, never to the vertical. Good. So our cast diagram is ready. Now we just have to read off our answers. So I can dispense with the calculator now. Go back onto the Word document. All right. So let's read off the angle. So for big X, remember we're going around twice. We start at 0 and we go around to 720 in that direction. So big X, we're going to have 180 subtract 60, which is of course 120 degrees. And you should be anticipating how many answers we're going to get. If we're going around twice, how many answers are we going to get? And you should be thinking 4. The next one, of course, would be 300, 60 less than 360. And we simply just have to add 360 to both of those. So we're going to have 480 for the next one, which is 360 plus 120. And 660 for the final one. So that's 360, add 300. So 660 degrees. So these are our X angles. Okay. Just to remind you, that corresponds to, this is equal to 2 theta. Okay. That's what the substitution we made earlier, which what we stated right at the beginning. So to get theta, I have to halve all my angles. Okay, so let's do that. So therefore, theta is going to be half of all these. So we just divide all these by 2. So we've got 60 degrees. Okay, 150 degrees, 240 degrees, and 330 degrees. So that this is looking good. Now, we've got to be careful now. Remember, initial step was we said here that we are going to do our working out in degrees, and then we can convert to radians at the end. So I'm just going to make a note of this. So now convert into radians to get our final answers. Do not forget that. Now, how do we do this? Well, just as a little reminder, remember that pi radians is equal to 180 degrees. So if I'm interested in what 1 degree is, I just divide both sides by 180. So 60 degrees would be essentially 60 pi over 180. So it's like I said in previous examples, all we have to do for this is write these as fractions of pi over 180. So we would have 60 degrees, but it would be out of 180. And that would be a multiple of pi, okay, for the first angle. Similarly, 150 degrees, but out of 180 and multiplying pi. And same all the way down. So 240 out of 180 multiplying pi. And we'll cancel these down in a second. And 330 out of 180 multiplying pi. So final step, just simplify all those. So classic one, pi over 3 for 60 degrees. That's the first angle. 1518 or 5 over 6 in its simplest form. So it's 5 pi. So divide by 30 essentially. 5 pi over 6. Then we've got 240 over 180, which simplifies to 4 over 3. So 4 pi over 3, dividing by 60, top and bottom. And then the last one, I'm going to have 11 pi over 6. Again, dividing by 60. So again, you can do that on your calculator if you need to. All right, so that concludes this lesson. Please try the exercises in the notes. And yeah, we'll see you in the next installment.